We're on to lesson 37, and now here's where we really get into atomic physics and models of the atom. And we start with J.J. Thomson's plum pudding model. Before J.J. Thomson, we have this guy, John Dalton, right here. And John Dalton is simply saying that elements are made up of atoms, and an atom is just like that. That's what an atom is. It's just a single unit of material, and it cannot be broken down into anything else. We know that's not quite the case anymore, but that was the early theory of early atomic theory by John Dalton. And then some of these other physicists like William Crookes and J.J. Thomson started to do experiments with cathode ray tubes. And I'm just going to go to YouTube here and just play this video in silence. And this is a cathode ray tube. And what you're seeing here is a stream of electrons going from a cathode right here, a negatively charged plate, over to an anode right here, a positively charged plate. Okay, and this is what J.J. Thomson did. He didn't know what he was looking at, really. He just thought he was dealing with a stream of particles. He didn't know what they were. And now what this person is doing, that's a magnet. And you can see that the magnet is deflecting. Let's see that again. You can see that the magnet is deflecting the stream of electrons. Wow, pretty cool. Electricity, magnetism, all that crazy stuff. And then this video just goes on to show different variations of the Crookes tube, cathode ray tubes, and so on. So that's essentially what it looks like. Let's get back onto our lesson. And you can read all these notes. Look at the diagram here. Here's the anode, cathode. And what happens is you put a high voltage between the anode and the cathode, and all of a sudden you get this beam of electrons that go across from the cathode to the anode. And again, J.J. Thomson, he didn't know really what he was looking at. So please read over all these notes. What he was looking at actually was just electrons. He was looking at a stream of electrons, and he didn't know that they were electrons, and he didn't know that they were negatively charged, but he was a pretty darn smart guy, and he did all these experiments. You can read out first and second experiment, but the third experiment is the one that we're really interested in. It says Thomson's third experiment was the most important and the one that he's most remembered for. It allowed him to measure properties of cathode rays. Cathode rays are just streams of electrons, specifically the charge to mass ratio. Charge to mass ratio. And why is that significant? Well, because remember, at this time, we didn't even know what electrons were. There was no such thing as an electron. And then, okay, so here's the apparatus that he used. So we have parallel plates over here that will create a voltage. And that voltage or potential difference will accelerate the electrons this way. And then they will go into this area here. This area here is called a velocity selector. So let's remember, you've got all these electrons. They're going into this, this velocity selector, and they all have different speeds. We have another set of parallel plates right down here, here. So they're going to create an electric field going down. So the electrons are going to be attracted up. The electrons are going to want to go up to the positive plate. But then you have a magnetic field, and this magnetic field is going into the board. So use your left-hand rule. And in your left-hand rule, your fingers will point into the board, your thumb will point to the right. And which way will the magnetic force be? It will be down. So let's just review that again. So the parallel plates here will make the electron want to go up. The magnetic field will want to make the electron go down. And if you balance those two forces, so you've got an electric force going up, you've got a magnetic force going down, and if you balance those so they're equal, what will the electron do? It'll go straight. Oh, but only electrons with a specific velocity will go straight. All the other ones that have a different velocity will be deflected either this way or this way. But only ones with a very specific velocity will go straight. Okay, let's work that out mathematically. So you can read over all the notes here. And then here it is. We have an electric force. And this is a good review of some of the formulas we've learned in electrostatics and magnetism. We have an electric force which will be defined as E times Q, the electric field strength times the charge. We have a magnetic force which is defined by QVB, and if those two forces are equal, then EQ equals QVB, and as you can see, the charge becomes irrelevant because it cancels out. And you get this derived formula. The velocity equals the electric field strength divided by the magnetic field strength. And it says in your notes, this is called a velocity selector because only electrons with a very specific velocity will have the electric field and the magnetic field balanced, and so only those ones will go straight. Any other velocity and one of these forces, the electric force or the magnetic force, will be stronger, and so the electron will not go straight, it will curve down towards or up towards one of the plates. All right, so here we go. Classic, easy example. You want to determine the velocity in an electric and magnetic field. If that's the magnetic field strength is 3.65 Teslas, and the field strength is 7.62. So without going through all the gory details, it's just this formula here. Plug the numbers in. And you get the answer, which turns out to be 2.07 times 10 to the 7. And then it says, explain the significance of your answer. Well, the only really significance of that answer is that it's about 10%. 10% the speed of light. And if you take university physics, you will discover that when things approach the speed of light, or that's not approaching, it's only 10% the speed of light. But when you're getting close to speed of light, really crazy things happen and you have to change your math. But that's for university. Oh, scary stuff. Okay, so yeah, it says moving faster than the 10% speed of light, and yeah, blah, blah, blah. Okay, now you've got electrons that have a specific velocity, and this is what Thomson did next. And this is why Thomson was a really smart guy. He turned off the electric field, so you've got electrons going at a very specific velocity, and now he turns off the electric field, so now they're going into a magnetic field only. And we know that when charged particles go into magnetic field, they will follow a circular path. So use your left-hand rule. This electron, magnetic field is going into the board. Electron is going to the right. Harm is facing down. Therefore, this electron will go in a nice circular path. And that circular path has a radius. So at this point, you can say that the magnetic force equals the centripetal force. And you get, just as we did for the velocity selector formula, we're going to plug in the variables. These are the two formulas we know for magnetic force and centripetal force. And then we're going to solve for Q over M. Why are we solving for Q over M? What kind of random thing is that, Q over M? Well, remember, at this point, we don't know what electrons are. We certainly don't know the charge of an electron. We definitely don't know the mass of an electron. So the best we can do is find out the ratio. We can measure velocity, we can measure radius, we can measure magnetic field strength, but we don't know Q and M of an electron because we really don't even know what an electron is. So the best we can do is find out the ratio of the charge to mass. QB equals MBR. Q over M equals, M goes down there, B goes down there. There it is. That's one of the most important formulas in physics 30. Q over M equals V over BR. It's fantastic because it shows us what we can theorize without knowing a lot of stuff. We don't know the charge, we don't know the mass, we don't know the nature of electrons, but we can figure out the charge to mass ratio. It's pretty darn ingenious. All right, so let's go to a specific problem. You decide to recreate Thomson's experiment to find the mass of an electron. You set up your cathode ray tube, blah, blah, blah. So you got a cathode, you got electric field, you got a magnetic field. You put the electrons through the magnetic field, electric field, and then you turn the electric field off and you measure the path of the electrons. So once again, you've got, let's just review the whole setup. You've got parallel plates here, positive, negative. You got an electron coming this way. You've got a magnetic field. Actually, I'm going to change it up just so you can think about this a little more. Negative, positive. So which way would your magnetic field have to be in this case? There's your electric field. So in other words, your electrons are going to go down. They want to go down towards the positive plate. So your magnetic field in this case is going to have to be out of the board. Out of the board, because now your fingers point out of the board, your thumb points to the right, and your palm goes up. So now your magnetic force is up. Your electric force is down. So if that was my configuration of having a positive plate down here, I'd have to have the magnetic field coming out of the board. So he does that and then turns off the plate. So now you've just got the magnetic field. Here's the velocity selector. Here's the magnetic field. Mag field. All right, and we are going to determine the charge to mass ratio in this, given this data. So the first thing we're going to do is find out the velocity. Step one is to calculate the velocity. And you've got all the values here. I'm not going to go through this in great detail. Here's the electric field strength. There's the magnetic field strength. If we divide those, we end up getting 3.21 times 10 to the 7 meters per second. And then step two is to just use the charge to mass ratio formula that we've just derived. And once again, all the information is given to you. Here's the magnetic field strength. Here's the radius. And here is the velocity. So plug those numbers in and you are going to get this kind of crazy number, which is 1.70 times 10 to the 11 times 10 to the 11 coulombs per kilogram, which should make your jaw drop. Why should that make your jaw drop? And just think about that number, 1.7 times 10 to the 11 coulombs. Remember, we said a bolt of lightning is about 1 or 2 coulombs is a bolt of lightning. And we're talking about 1.7 times 10 to the, there's a lot of zeros over there, coulombs per kilogram. Why is it such a big number? Because we're talking about a kilogram of electrons. How many electrons is in a kilogram? I have no idea, but it's billions upon trillions and zillions and gazillions. It's a lot. There's a lot of electrons in 1 kilogram. That's why it's so much charge. And then the last part of the question says, determine and compare it to the accepted value. So the accepted value is of charge to mass. We know from our formula sheet that this is the charge of an electron. And we know that this is the mass of an electron. And if we divide them, we get that as our charge to mass ratio. So in this experiment, we were pretty close, 1.76 compared to 1.70, which if you do that as a percent error, I think you get 3.08% error. Not bad at all. Okay, and so as a result of all this, the cathode ray experiments, charge to mass ratio, we come up with this theory. This is J.J. Thomson's plum pudding model of the atom. And now instead of the atom just being one single thing, it is one single thing with, right here, with a lot of, it is one big blob of positiveness with all these random negatively charged electrons in it. Okay, and we didn't even call them electrons at that point. They just say that the atom is a big blob of positive material, and there's all this negative material, these little points of negative material in that blob, and they balance each other out to become neutral. So that is Thomson's plum pudding model of the atom. And then the last thing it says, although we know it's wrong, at the time it was the first model to take into account separate negative and positive charges. Amen.